on how to do some optimization with Solver. So we're going to be focusing once again very much on the basics here. The goal is to know how to do linear programs at the end of the week for those of you who are interested. So just as a reminder, this is highly non-mandatory. It's just for those of you who have already got a very good background in math and who would like to learn more over the course of the week than what we cover in class. So you may find this useful, but I repeat, this is highly non-mandatory. So let's get started on some basics that will enable you to do some exercises relating to this topic. So let me start off with what optimization is. So optimization, broadly speaking, is about making the most out of any possible situation. So you, in your life, you routinely solve many optimization problems in your everyday life. So for example, when you decide what to eat at lunch, right? You might want to maximize your healthiness or maybe maximize your pleasure if you're more of an Epicurean. You could have, so you want to maximize some sort of objective, subject to what we call some constraints possibly. So you don't want to eat the same thing as yesterday. You want to stay under a certain level of fat or sugariness. Or you don't want to eat something, if this is maybe an interview, that you could spill on yourself. So this is a typical example of you solving an optimization problem very, very frequently in your day-to-day life. Another example is, for example, how do I organize my week? So you may want to maximize the long periods where you do nothing. But then you have constraints. You have a certain amount of homework that has to be done. You have a certain amount maybe of socializing that has to be done. You don't want to work on Saturday evenings or on Sundays. Maybe you have some constraints around how things are scheduled. For example, you have to always schedule a shower after working out. So these kind of scenarios. So as you can see here, what's coming up around optimization is the fact that we're always trying to have either maximize or minimize some kind of objective subject to some constraints. So optimization is also routinely used in businesses. I'm going to give a couple of examples now. So let me start off with Netflix's recommendation system. So here, this is my Netflix account. So I'm sure you all know what Netflix is. No need to explain that. So if you go to your Netflix account, you'll see examples of, you'll see their recommendation system. So these are the movies that they think you should be watching because you liked other movies. So in my case, I have 3 movies that are given to me here that are recommended to me. So the way that they've chosen these movies to show to me is they want to maximize the chance that I will actually go ahead and watch one of these movies. And there's subject to some constraints here. They can't show me movies I've already seen because otherwise I won't go necessarily rewatch them. There's a limited amount of space, so they can only show me maybe maximum of 10 movies. So again, this is an optimization problem that this business is solving. Other places where optimization is used is Amazon package delivery. So Amazon uses a lot of optimization. But its package delivery is a great example. So typically what they're trying to optimize when they're trying to get the package to you is the cost to deliver the package. So they're trying to minimize that cost, but they are subject to a lot of different constraints. So it can't take more than a couple of days. They can't go through warehouses which are full or closed, right? Especially during lockdown, for example. And it must arrive at the particular time and date that they specified to me or that I specified if I'm, for example, a Prime customer. So this is another example for Amazon package delivery. There are many other examples. I'm not going to go all over them, but for example, in finance, you know how to invest money into stocks to maximize profit, revenue management and pricing, so how to price tickets or goods, for example, airplane tickets, so as to maximize maybe occupancy, also as to minimize the amount that you're throwing away. Resource allocation, so how can you allocate goods, rooms, staff, personnel, while respecting everyone's constraints? Then there's the question of routing, so shortest path to take typically. So Google Maps is built on an optimization module. So shortest path to take with different constraints, maybe depending on traffic, these kind of things. Facility location is another example of an optimization problem that you're solving. So where do I construct a new facility? Which facilities can I close if I have many? So these kind of scenarios are all guided by optimization. So we're going to start off with some very easy examples. These are kind of end of the line kind of optimization problems. So we're going to start off with some easy examples. And before I get to that, I want to tell you about the building blocks of optimization. So all these examples that we've seen before as we discussed, have three commonalities. And these are what we call the building blocks of optimization. And when you build a model of a problem with an optimization model, you need to really, really think about these because they'll condition your solution. So the first part that is the same for every single problem we've seen so far is what we call decision variables. Now, these are the things that you always start with. You always work out what you're making a decision about. So these are the decision variables. It's what you have control over to change. It's the alternatives you can choose among many. Now, you always start with decision variables because that is actually the trickiest part in an optimization problem, is working out what those are. Once you have your decision variables, it becomes a lot easier to go ahead and model the constraints and the objective. So decision variables is what you always start with. Then you have the objective. So that's the quantity that you're trying to maximize or minimize, okay? And then you have the constraints. Those are the kind of restrictions that you're imposing on your decision variables. So that was all about what an optimization problem is. So we remember decision variables first, then objective, then constraints. Okay, that's how you build an optimization problem. You can switch around constraints and objective values if you so wish. That's not very important. What is important is to always start with the decision variables. Now, how do we go about solving optimization problems? Once we've written the problem down, we're maximizing some constraints and maximizing some objective subject to some constraints. And we want to find these decision variables that maximize my objective and that are feasible for the constraints. How do we do this? We do what we call solving the optimization problem. So that gives you the decision variables that work for your problem and that maximize or minimize your objective. Now, to solve an optimization problem, we're going to use Solver, and we're going to see how this works on an example. So this is the example that we're considering. It's a very simple distribution example. So imagine that you direct the logistics for a firm that produces and manages one single product, two different plants, P1 here and P2. P1 and P2 have different capacities. Here P1 has got a capacity of 200,000 and P2 here has got a capacity of 60,000. Both plants interact with warehouses, and both warehouses have equal holding costs. Now, the specificities of each warehouse is that warehouse W1 is close to your plant, whereas warehouse W2 is close to customers. And we have the following costs, okay? To ship from plant 1 to W1, it costs us no money whatsoever because they're so close. To ship from P2 to W1, on the other hand, costs us $4. And then we also have the problematic, once we've done, once we've stocked our product in the warehouses, W1 and W2, we then need to shift to the customer regions, C1, C2, C3, where we need to meet demand. So demand here is 50,000 for C1, 100,000 for C2, and 50,000 for C3. So the idea here maybe is to set up a scenario, right, where we're shipping some amount between P1 and W1, and then W1 and all the regions. And the question is, which one can be done? So what can be done? How many units do we need to ship between P1 and W1, and W1, C1, C2, and C3, and P2 and W1, and so on and so forth, to minimize cost here? So that's the goal. So optimization would do this for you automatically. Let's see if there's a way that we can go about this in an intuitive way and bypass the optimization part and not actually have to solve it on a computer, just do it by hand. Now let's think about a couple of ideas. So one idea you could have, an immediate idea as to how you could ship your product, is maybe just ship everything to the warehouse that's closest to the market, because then you have low dispatch costs to the different customer areas from the warehouse. So in that scenario, because I need to meet demand here and I can't go over capacity in these two scenarios, I'm going to produce the maximum here, 60,000, because it only cost me $2 to ship to the warehouse 2. And then from the warehouse 2, I'm going to ship everything out. And I'm going to produce also some in P1, so 140,000 in P1. So that way I can meet demand in C1, C2, and C3. So if we go forward with that solution, so we're completely bypassing warehouse 1, the total cost of this strategy is going to be 1,120,000. Is that the best? Possibly not. So let's think about another idea. So we're going to think about dispatching based on the minimum to market cost. So if I took a look at C1 here, and I take a look at the path that brings me the smallest costs to meet the demand in C1. So if we take a look, we can have many ways of getting to C1. So either we can go for P1, W1, and then end up at C1. That has a cost of $3. Or we can go for P1, W2, and then C1. That's a cost of $7. Or we can go from P2 to W1 to C1. $7 again. Or we can go from P2 to W2 to C1. That's $4. So in this case, the minimum to market cost is the $3 here, and so we'll push everything from P1 to W1 to C1. So we'll push the full 50,000 that C1 needs from P1 to W1 to C1. Okay, we've taken care of C1. Demand is met at C1. We now move on to C2. Now for C2, we need 100,000 units to arrive there, and there's many ways of getting to it once again, all with different costs. And if I take a look here, this one that gives me the smallest cost is via P2 and W2. Great, right? This is a path we haven't used that yet. So I'm going to go through that scenario to ship to C2. Unfortunately, P2 here is limited in capacity. I can only actually produce 60,000 units here. So I'm going to produce my full 60,000 and ship to C2. And the rest, well, I'm going to have to ship via P1. So I'm going to have to take from P1. So I'm going to add whatever's missing here, the 40,000, to P1, ship it through W1, and then ship it to C2, because that's the second cheapest option here. Okay. And then for C3, I do a similar thing. I take a look at what's the cheapest option for me. So it should be P2 to W2 to C3. Unfortunately, P2 is already producing at the maximum of its capacity, so that can't work. So we now move on to P1 W1 C3, which is the second cheapest. And this is the one we're going to go with because we can still produce 50,000 here, which corresponds to the demand in C3. So we can produce that amount, right? It's 50,000 here. And then we make it transit through W1 and then all the way to C3. So this is one particular way we could ship, and it's based on what we call the min to market cost, okay? So it looks at the shortest, the path that costs us the less for each consumer region. Now the question is this optimal, right? The total cost of this strategy is $790,000. And the question is, can we do better? So it's certainly better than the previous strategy we had. And I'm going to answer your question now as to whether it's better, we can do better. And the answer is yes. Actually, the optimal way of allocating the shipping quantities here gives us a cost of 740,000. So again here, 50,000. So how to find it? First step is going to be about formulating the problem. So let's try and do that now. So how are we going to formulate this problem? So I know this looks really panic-inducing. It's not. Let's pass this. So what are going to be our decision variables here? Well, exactly what we were trying to decide on in the previous scenario, right? How much we ship from one place to another. From the plants to the warehouses, so from P1 to W1, from P1 to W2, from P2 to W1, and from P2 to W2. Here we have 4 different quantities. Here, it's from the warehouses to the customers. We have 6 different quantities. So in total, we have 10 what we call decision variables. And these decision variables are simply how much we ship from one place to another. Now, in terms of constraints, we have a couple of constraints that we need to meet. The first one is about capacity in each warehouse, right? In each plant, sorry. So in each plant, production is capped at 200,000 for P1 and 60,000 for P2. So we just sum whatever's going out of P1, so whatever goes from P1 to W1 and P1 to W2, and we impose that this be smaller than 200,000. Same thing for everything that goes out of P2. We impose that it be less than 60,000. The demand here also has to be satisfied. So whatever we ship to C1 has to be greater or equal to 50,000. Likewise for C2, greater or equal to 100,000. And likewise for C3, greater than 50,000. Now we have 2 specific quantities here, W1 and W2. which is we can't suddenly create product at W1. So whatever goes into W1 has to come out of W1. So whatever we're pushing in to W1 has to come out of it. Similarly for W2. So these are what we call the flow constraints, okay? They force, it means that you're not stocking and not creating anything in the warehouses, which makes sense. And finally, we want every single one of these conditions to be non-negative. So these are the constraints. We're just missing the objective, which is the cost. So for that, we just take our quantities and look at how much it costs us to ship from P1 to W1. And we multiply that by the amount we're shipping from P1 to W1. So here it costs us nothing to ship from P1 to W1. So we multiply this decision variable by 0. It costs us 5 to ship from P1 to W2. So we multiply the quantity here by the cost per quantity. And so on and so forth. So this gives us our cost. So our goal here is to minimize this cost with these constraints. Now, how do we solve this problem? We've set it up and we've got it running. So we've got the model all set up, all good. We know what our decision variables are. We know what our constraints are, and we know what our objective is. The question is, how do we solve this now? So we could try to solve this manually, as we saw. We could try plugging in different possible solutions, trying to find intelligent ways of coming up with the right solution. But this would take typically a long time, and this is a really small problem, right? We only have 2 warehouses. We only have, a couple of customer regions, a couple of production plants. So it's a very easy scenario. Now, if you went to a much more complicated scenario, and I think this is still too easy, right? You have massive scenarios where you have a ton of decision variables. You wouldn't be able to do this anymore. So there has to be an automated way of doing this. And to do this, we require what we call a solver. Now, there are many different solvers that exist out there. The one I'm going to talk to you about is in Excel. So it's the solver in Excel. Do bear in mind that there are ways of doing this that use, for example, Python. So any solver takes an optimization problem as input in a standard form and outputs a solution. So I'm going to focus on Solver in Excel, which is an add-in to Excel, and it's more visual and it can be very useful for you, especially if you know Excel well already. So what to do next? So I encourage you to watch the video on how to install Solver, so how to activate the Solver in your Excel. Then watch the video on how to use Solver to solve the distribution problem we just saw. These are all available on the course platform. I'm now going to move on to talking a little bit about the type of optimization problems that Solver solves. So Solver only solves 2 types of optimization problems: linear and integer programs. Now we're going to talk about linear programs moving forward. If you want me to do a quick video on integer programs, do let me know. I'm going to first focus on linear programs because that's the most basic one. So we're going to see what that is now, and then you'll be able to do exercises on linear programs. So linear programming. What is a linear program? So of course you can probably see, right, that not all optimization problems are necessarily easy to solve. There's a difference in complexity between optimization problems. And there's many different factors that drive the solving time and the quality of the solution that you obtain. So of course there's whatever's used as your algorithm in Solver. There's the number of variables and the number of constraints that intervene. Certainly, as you scale up the number of variables, it becomes more complicated to solve. But actually, the most important thing by far that really conditions how good the solver can be in solving the problem is what we call the constraint and objective types. So it's the way the constraint and the objective depend on the decision variables. So depending on the type of constraints and objectives, so depending on the way you write the constraints and the objective with the decision variables, it can take infinitely long to get a solution. That's why linear programming is super important. It's because it's one of those scenarios where we actually know that we can solve things very fast and the solution we get is known to be the best solution possible. So that's why we're going to focus on it now. So what is a linear program? So a linear program is an optimization problem that has constraints that are linear combinations of the decision variables. So what does that mean? If x1 through xn are my decision variables in optimization, the only thing I'm allowed to do with them is multiply them by numbers and add them together. And then we can have that constraint be less than or equal to 0, greater or equal to 0, or equal to 0. That I don't mind about on this side. But what is super important is I can't have, for example, x1 squared. I can't have x1 times x2. I can only do these linear combination of the decision variables. So this is what the constraints have to look like. Similarly, the objective has to be, again, a linear combination of the decision variables. So I'm only allowed to take the decision variables, multiply them by some numbers, and add them together. That's the only thing I'm allowed to do with my decision variables. When we have this kind of structure to our optimization problem, this is what we call a linear program. And we're able to solve linear programs really fast, and we can guarantee that the solution we obtain is correct. Okay, so what to do next? The only way to get really good at writing down linear programs and solving them is to practice, 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 just like coding. So now, after you've installed Solver, taken a look at the distribution example in Solver, how to solve it, please move on to the linear programming exercises. So there I'm going to ask you to read the problem, model it like a linear program. So write down the decision variables, the constraint, the objective for each situation that you're given. Once you have that working nicely, move on to Solver and try to actually solve these problems. The solutions are also given on the course platform. Good luck.